All right. Well, welcome everyone. We're going to be talking about low integrity protection layers. So where all this started was customer requests for information on what do I do with interlocks that are not safety instrumented functions. And how do I design them? How do I document the design? How often do I test things? And specifically, the question was related to shutoff valves. So, especially in the oil and gas, offshore oil and gas industry, there are a lot of situations where you have shutdown switches all over the place. And when you hit the shutdown switch, you're going to close valves. Now, that technically does not, well, technically, it can be considered a safety instrumented function, but historically, it is not considered a safety instrumented function. So let me go ahead and share my desktop, and I'm going to be jumping all over the place between standards, between presentations, between technical reports, between standards that will be, standards that might be, and so on. So what I'm going to be kind of hinging off of is this non-SIS IPL testing guidelines, which is a presentation that I put together with Rory and Matt from Kenexis, and also the driver for this was a Mr. Yasser Khalil from Zadco. Zadco is now ADNOC offshore with the consolidation. So out there in Abu Dhabi, when we were doing kind of SIS design basis for the plant as a whole, and the P&IDs are showing these safety critical alarms. The P&IDs are showing push buttons that close valves, but they're not complete entire loops. They're not complete entire safety instrumented functions. So how do we deal with that? And we went back into IEC 61508 to do some thinking. We went back into the LOPA books to do some thinking. We researched other standards that are specific to alarms, and we kind of came up with an approach for what would be the most appropriate way to handle things. This was back, so we started these discussions in 2009, and this paper was presented at an ISA conference in 2010. Now, I'm going to kind of focus on this, but there are a couple of other things that I am going to get ready to go. So one of the things I'm going to get ready to go is this document. So this was a draft, and this was back 2024, 2025 timeframe. So what you're looking at has been revised, and it's been approved. There's still arguments about it, but it is a standard from the ISA 84 committee for what originally started out as SCI, safety controls, alarms, and interlocks, and that got converted into PSCI, process safety controls, alarms, and interlocks. And now it's been finally renamed the least attractive of all the potential names. It is the LIPL, or the low integrity protection layer. So we're talking about how we're going to handle low integrity protection layers. And I'm going to focus on how do I do the design and how do I set the test intervals. That's going to be kind of the most important portion of it, but there's more to it than just that. So we're going to look at this ISA standard. I am also going to go to the mother document of everything, and I'm going to look at the OSHA PSM standard to see, well, what does the government say about this in the US? And I'm going to refer to OSHA PSM, but globally, the same concepts apply, whether it's COMA in the UK, Seveso, anywhere you're at in the world, things get done roughly the same way. So that'll kind of lead you into that. So we're going to be looking at that. And we are also going to go into the IEC 61511 standard, because we're gonna be looking at some definitions. So and then later on, I'm going to even open up the Kenexis OpenPHA tool and the Kenexis Vertigo tool to show you, well, how should you be documenting all these things at the end of the day? So first things first, let's go ahead and pop into the presentation and kind of start the discussion there, and we will meander around to all these other documents as we progress. So non-SIS IPL testing requirements, and the non-SIS IPL became SCI, which became PSCI, which is now LIPL, low integrity protection layers, because it's a low integrity protection layer if the risk reduction factor is equal to 10 or less. Now, you might be thinking that equal to 10 is a SIL 1 safety instrumented function. Yes, it is, but at the same time, no, it's not. It has to be greater than 10 once we look into the definitions. All right, so safety critical instrumentation. In your process plants out there in the process world, whether it's oil and gas, refining, upgrading, petrochemicals, specialty chemicals, pharmaceuticals, you have instrumentation to run that plant, and that instrumentation is going to fall into two basic categories. That is going to be your basic process control system, which is the equipment that is used to keep the process in its normal operating limits and also provide feedback to human operators on what the status of the plant is. So indicators of temperature, pressure, flow rate, etc. Now, there's the starting point in the journey of safety critical instrumentation, which leads us into safety instrumented system design, is, well, what is safety critical and what is not safety critical? Because if you have safety critical instrumentation, our good friends at the Occupational Safety and Health Administration have written a rule, the Process Safety Management Rule 29 CFR 1910.119. They've written rules for how you need to design and maintain and document and test that equipment. Okay, so in a nutshell, the OSHA PSM standard says that this safety critical equipment needs to be inspected and tested such that it follows RAG-GEP, or some people call this RAG-GEP. The acronym is Recognized and Generally Accepted Good Engineering Practices. So I go with RAG-GEP. So the regulation says that you need to do something about safety critical equipment. You need a mechanical integrity program, but it doesn't define the exact nature and frequency of the testing. So back in the prehistoric days, when I first started my career back in the early 90s, the OSHA PSM regulation just came into effect in 1992. That happens to be the same year I graduated from college. And a lot of the plant operators just didn't know what to do with this regulation. They said, well, we need to inspect and test our safety critical equipment. So let's just once a year. There you go. A decision has been made. Well, it turns out that's an absolutely horrible decision because that's a whole lot more testing than you probably need. There is no rational basis. You just pulled a number out of thin air or other places. So maybe we should have a more rational and credible basis for how often we're going to test things, because the plant managers quickly realize that this is costing them a fortune. And if my oil refinery is only shut down once every 5 years for a turnaround, how do I test this equipment while the plant's online and running? Well, most of the time you can't. So what the heck do I do? Okay, so this is our first pause point. Let's go back to the OSHA PSM standard and see what it says. Here is the actual standard, the actual Code of Federal Regulations. Again, this is US, but wherever you're at in the world, it's going to look fairly similar to this. So OSHA has it's not a law, but they have the authority to take you to jail and fine you if you don't follow their regulations. So it has the weight of law. So with process safety management of highly hazardous chemicals, there is a very large variety of things that you need to do. If you're a covered facility, which most chemical plants are going to be covered simply due to the amount of flammable materials that they have. So the PSM rule is going to have a lot of attributes to it. The employees need to participate. You need to develop process safety information. And if we keep scrolling along here, process hazards analysis, we're going to get to clause J, which is mechanical integrity. So if you ever wondered why we pick SIL targets and run SIL verification calculations, have no doubt it is OSHA PSM rule, clause J, mechanical integrity. So in this mechanical integrity clause, it says that you need to have a mechanical integrity program for the following pieces of process equipment, and that's going to include controls, including sensors, alarms, and interlocks. So we need to have a mechanical integrity program for our controls that includes written procedures for how to operate and maintain the equipment. People need to be trained on how to operate and maintain the equipment. You need to perform inspection and testing of this equipment. And here is, some of the attributes of the inspection and testing. You need to correct deficiencies that you find during inspection and testing. You need quality assurance of all of this stuff that is going on. So it's telling you that you need to do a lot of stuff, but at the same time, it's not giving you any specifics. It doesn't say that if you have a push button that closes a valve, you need to test it once a year. Well, OSHA is, I don't want to say they're notorious for this because that would kind of be pejorative. It's a good thing that OSHA doesn't get into the detail of saying, okay, for a push button, you're going to want to test it once every 47 days. Nobody wants OSHA doing that. Instead, they have this item right here. And you remember that ragagep thing? This is where it comes from, straight from the man down to you. Inspection and testing procedures shall follow recognized and generally accepted good engineering practices. So I've shown you the entire clause out of the OSHA PSM standard that is kind of the genesis of SIL verification calculations, SRS, and everything that has ever happened. And as a matter of fact, this clause is the driver for how the ISA 84 standard that was released in 1996 was developed, because OSHA is relying on groups like ISA, ASME, API, and FPA to create these recognized and generally accepted good engineering practices. And ISA 84, IEC 61511 are examples of recognized and generally accepted good engineering practices for safety instrumented systems. But immediately we get into a little bit of a glitch because, well, what is a safety instrumented function? Is a safety critical alarm a safety instrumented function? Is a push button that closes a valve a safety instrumented function? Because if you're following ISA IEC 61511, you've got a very long, elaborate procedure that tells you you need to do a risk analysis, you need to pick a target, you need to quantitatively verify that your design achieves that target. And that, for sure, you need to do that for safety instrumented functions. But what do you do if it's not a safety instrumented function? And the first sticking point that we ever got into is, well, do I need to do this mechanical integrity program for every instrument in my plant? I mean, I have a pressure gauge that's measuring the pressure, of utility steam. Do I need to have a inspection testing program? Do I need to do SIL verification calculations for every relief valve? Or I'm sorry, not every relief valve, every pressure indicator, every pressure gauge? Well, the industry said, oh, hell no. We are not going to put together a mechanical integrity program for all of the equipment, for all of the controls. We are only going to put together mechanical integrity programs for controls that are safety critical. So where did we throw this down? Well, we created a recognized and generally accepted good engineering practice called ISA 849101. So let's pop open that document. Let me open it up and show you generally what's in here. It's a really short document. It's mostly credits and intentionally blank pages. And a forward, and then finally we're going to get into our requirements, where it basically says the first thing that we're going to do is we're going to look at all the equipment in our plant and decide what is safety critical and what is not safety critical. That's what the scope of the standard says. We're going to address what is classified as a safeguard as opposed to basic process control. And then only are we going to create a mechanical integrity program for the safety critical stuff. So this is the standard, because right out of the gate, OSHA was handing out fines to people because they didn't have test records for every pressure gauge in their plant, which is absolutely nutso, which is why we wrote this. Now, we're looking at the 2012 version. The first version was early 90s. It was originally released. So we're going to define some things. So we've got this antiquated safety controls, alarms, and interlocks. And then we kind of have a list of the different things that we would consider safety instrumentation. So there are safety instrumented systems, but there are basic process control system interlocks, there are permissives, there are alarms, there are manual push buttons, there are detection and suppression systems, which may not be a safety instrumented system, but it is still safety critical. It's something that we take credit for when we're doing our risk analyses, when we're doing our layer of protection analysis. So for the identification process, our safety, our SCI are going to be identified and documented in a manner that clearly distinguishes them from other instrumented systems. How is that going to happen? Well, the bottom line is you're going to do a LOPA, and if you take credit for that piece of instrumentation in your LOPA, it is safety critical. So let's start out with a question already from Mr. Bill Hartz. Dave,
hey,
ask me a question.
So just to kind of your last statement and kind of what you were saying before that, are these only for when you're taking an IPL credit for it, or could this be further expanded into any safeguard that you take, even, qualitative credit for in the, presence of a PHA or HAZOP type situation?
Very good question. And the answer is it can be whatever you want it to be. You just need to be consistent. So there are some companies that will go through their P&IDs and kind of mark them and say, okay, this is safety critical, this is not safety critical. There are other organizations that will kind of have a standard that says based on the use of the equipment, it is safety critical or not. But hands down, the most common way is that I did a risk analysis and I credited this safeguard in my risk analysis. So if you're doing the HAZOP LOPA process that's most common in industry, you did a HAZOP and a high consequence scenario or a scenario of interest was brought over to LOPA, and in LOPA, I took credit for that instrument as a safeguard. That's the most common way to distinguish what is safety critical and what is not safety critical. But you'll note that this standard simply says that you're going to identify and document it. It doesn't say how you're going to identify it and document it. So the people that do it in the LOPA, that's their approach. Some people just kind of get highlighters and mark up their P&IDs. That's a different approach. Both of them are acceptable in accordance with this standard. Okay, so once you determine that something is safety critical, then you need to install it properly, you need to maintain it, you need to do inspections to test it, and that's it. I mean, this whole standard is, if you take this, it's 4 pages maybe of text, and if you take the figures and the definitions out, it's about like a page and a half of meat. Document what is safety critical, and then make sure that you test it and document your tests. Okay, so great. I know that if I take credit now, and I'm going to kind of go back to a certain approach where I'm going to do HAZOP to LOPA, and I'm going to take credit for safeguards in my LOPA. And if I take credit for a safeguard in my LOPA, I know that it is safety critical, which means I need to do testing, et cetera, et cetera, et cetera. Okay, so that's where we're at. Now, the question is, if something is safety critical, how do you determine how often to test it and what the design looks like? If your safety control alarm and interlock is a safety instrumented function, you have the IEC 61511 standard to follow. But is a safety critical alarm the same thing? Is a push button that causes a valve to close the same thing? I'm going to say absolutely no, it's not. And I'm always right. So, what else do you need to know? It is because I told you so. But in case you're like me and you want some proof and you want to make this decision for yourself, let's drill down again into the source documents. So I'm opening up now my copy of IEC 61511. I'm going to go up into clause 3 into the definitions. And what definition do you think I am going to go to? It is going to be the definition of here in the semi-alphabetical section 3. Safety, integrity level, safety integrity, safety instrumented system. There it is. Okay. So if I'm looking at, and again, the light bulbs that we're going to be focusing on are really the big dogs are safety critical alarms and push buttons that close valves. How do I design those things? Do I use 1511 to design them? My answer is no, you don't. So how do I justify not doing that? Well, you need to read through the 61511 standard and convince yourself that an alarm and a push button is not a safety instrumented function. Trust me, you do not want to design alarms and push buttons in accordance with the 1511 standard because it's designed for a complete automated system. All right, let's go to the definitions. The first one is safety instrumented system, which is an instrumented system used to implement one or more SIFs. Absolutely clear as mud. All right, we're going to need to now go into the definition of a SIF. But before I do that, let's go look at the notes and go all the way back to when I joined the ISA 84 committee back in 1994, before the release of the first functional safety standard. In the original OG functional safety standard, we defined the safety function as a function, a system composed of a combination of sensors, logic solvers, and final elements. It also includes blah, blah, blah. So basically, what we said was a safety instrumented system is a system composed of sensors, logic solvers, and final elements that will move the process to the safe state when an abnormal event is detected, or when a demand is detected, or when a hazard is detected. The key when we were writing the standard was that a safety function is a complete loop. It's going to automatically detect that the process has gone out of control and automatically bring you to a safe state. No human beings in the middle. So that would mean, according to that old original definition, a safety critical alarm is not going to be a safety instrumented function because it doesn't take you to a safe state. A push button that closes a valve is not a safety instrumented function because it doesn't detect that the process has gone out of control. Furthermore, those subsystems have other standards that define their design. So if you're looking at the push button that closes a valve, there are rules in ANSI standards for machine tools for how to do that emergency stop circuit. There are rules in API 553, which is a control valve standard, for how to design an emergency remote operated block valve, and how you would design the fireproofing and all the other attributes in between the push button and the valve itself. So there are other recognized and generally accepted good engineering practice to define how to design those systems. And on the sensor side, for the alarms, let me assure you, the fine folks of the ISA 18 committee are going to be the first people to jump up and down and tell you that an alarm is not a safety instrumented function you design per ISA 18, not per IEC 61511. So anyway, the mud in the water here, though, is that it says any combination. So let me, as a member of the IEC 61511 committee, let me give you a little bit of the inside story on how standards are written. Number one, of the time the committee spends talking about a standard, about 40% is the requirements and about 60% is definitions. So we spend a lot of time arguing over definitions because definitions are super high stakes. Now, when we're arguing about definitions, if two people have diametrically opposed views, what ends up happening is the definition gets diluted and confused until both people can read that definition and think that it means what they want it to mean. So those are some of the immutable laws of standards writing, and why when you look at a definition in a standard, you're more confused than before you read the definition. But let's keep doing a little bit of digging. So a safety instrumented system is an instrumented system used to implement one or more SIFs, which could be any combination of sensors, logic solvers, and final elements. But in order to know the definition of a SIS, we need to know the definition of a SIF. So what is a SIF? A SIF is a safety function to be implemented by a safety instrumented system. Okay, well, this doesn't help me until I know what a safety function is, so I keep going. A safety function is a function to be implemented by one or more protection layers, gotta love that, which is intended to achieve or maintain a safe state for the process with respect to a specific hazardous event. So the way I'm reading this, a safety function needs to achieve the safe state. That means it has to contain the final element with respect to a hazardous event. So it has to know that the hazardous event is happening. So I'm going to argue, and virtually every SIS expert I have ever talked to tells me that you have to have a full automatic loop to be considered a safety instrumented function. That means alarms are off the table, push buttons that close valves are off the table. We're going to need a different approach to pick performance targets and verify that the performance targets are achieved. And hopefully we could do that in a way that's very cost efficient and effective and not too labor intensive. So while you can read these standards and say, hey, this alarm needs to get a SIL, most people are going to disagree with you on that. And as I've shown you these muddy definitions, I can kind of twist this to say anything that I want it to. But industry, the consensus is I need a complete automatic loop from sensor to final element in order for it to be considered a safety instrumented function. Now, as soon as I say that, I'm going to have permissives, which are kind of weird, but that's a discussion for another day. So right now, coming back into the presentation, OSHA said that we need to put together mechanical integrity programs for our safety critical equipment. The ISA 849101 standard told me that, well, I can define what is safety and what is not safety using a standard process. The most common process in industry is HAZOP, LOPA, and if you have taken credit for an instrument in a LOPA, it is safety critical, and I need a mechanical integrity program for that device. Now, if that device is a safety instrument and function, you've got IEC 61511, and there are years of videos on YouTube explaining how to deal with that. But now, if it's an alarm or if it's a push button, I'm kind of in a nebulous area. What do I do about that? Well, this slide is going to give you, so this kind of predated Sky. We were just SCI, safety critical instrumentation. We talked about 1511, but alarms have ISA 18.1 and 18.2, which, unless something has changed, don't tell you how often you're going to need to test something and how it needs to be designed. So that's kind of a weakness there. API 553 talks about some of the design attributes of emergency block valves, but once again, doesn't tell you how often you need to test it, whether you need double block valves or single block valves. And then, there are other examples of safety critical instruments, relief valves, remote operated valve, rupture discs, etc. Okay, so everybody has seen this slide before, and this kind of goes back a little bit to, well, how do I determine whether something is safety critical or not? And when you do your HAZOP, you're going to identify safeguards. When you do your LOPA, you're going to qualify those safeguards as, is this something that I am going to hang my hat on? Am I going to take credit for this safeguard as a something that will reduce risk to a tolerable level? And if I do that, now there's an extra higher level of care that I need to apply to this component. And here is, wow, this is a very old, it is over 15 years old, this presentation. But here's an example of a LOPA. We have a low level causing gas blowby. You have consequences. You're going to have your design target initiating events, and then you're going to have protection layers. So here we've credited two protection layers, one being a safety function, and it needs to achieve a PFD of 0.1. Now, we've also defined another protection layer called operator intervention based on alarm. And guess what? We have also assigned it a performance target. But this is a little bit sloppy, because operator intervention is a lot of things. It's going to be the sensor. It's going to be the annunciation. It's going to be the operator that needs to acknowledge, diagnose, and respond to the alarm. And it's also the equipment that the operator manipulates to get back to a safe state. So this 0.1 is something that is very commonly used for operator intervention as a safeguard. And that number of 0.1 is ubiquitous. It is almost the only number that's ever used. So what is the disconnect between the fact that I've already said my alarm needs to get me a PFD of 0.1 and the design and the testing attributes? Well, it's because, well, number one, nobody's forced me historically. Whereas in the past, OSHA has asked me for SIL verification calculations and SRSs if something is a safety instrumented function. But for alarms, well, historically, they haven't looked for that. But more and more, they are looking for that. So now what do? I know that this guy here, I'm going to follow my IEC 61511 workflow. Certainly. But now for this guy, what is my workflow? Well, it turns out as of this year, your workflow is going to be ISA 849103. 03 is our good friend that I introduced you to earlier, this is the LIPL, the Low Integrity Protection Layer standard, which has been the source of a lot of arguments, the source of a lot of controversy, but it's out there. It's been released as a standard. We will see if it actually gets adopted by industry and becomes recognized and generally accepted. It's been released, but it's up to industry to determine whether they are going to generally accept that standard that has been written by ISA. Okay, so let me clear out. There's a little bit more text on this slide. So if it's a safety instrumented function, 1511 is the way to go. You know what your PFD is. You're going to calculate your test interval based on what equipment you're using, voting arrangements, diagnostics, etc., to be able to achieve that target. So the question is, can we apply the same principles to other IPLs without going to all the trouble of being fully 61511 compliant and only being LIPL compliant? And the answer is yes. You're going to have a lot more flexibility to do things with lookup tables and so on. So let's dig into the details. So SIS versus non-SIS. A safety function is the complete kit. We're going to be able to detect that you are out of control. We are going to be able to think about the fact that we're out of control and decide what to do about it. And then we're going to be able to actually take the action that is going to allow me to get to a safe state. Whereas some of the other independent protection layers, it's bits and pieces. So non-SIS safeguards usually don't form a complete function. So if an operator needs to close an isolation valve on the detection of a fire, well, there's got to be some sort of sensor to let the operator know that a fire is present. Then that sensor is going to get wired maybe into the DCS, maybe into a local fire panel. It could end up in a lot of different places. And then there's an isolation valve that maybe is going to be manually operated. Maybe the operator is going to push a button on the DCS. Maybe they're going to go out in the field and push a push button. A lot of different options, but these are their own separate pieces that generally don't talk to each other. So if I'm looking at operator intervention based on an alarm, same thing. I have the sensor and I have the alarm. So I can even put in another device here called the annunciator. So that annunciator, it might be a panel arm light. It might be a horn and a siren out in the field. It might be a blinking light on the DCS screen. Now, in terms of the operator intervention, the logic solver is going to be the original neural network, the natural intelligence of the operator's brain trying to diagnose whether the alarm is real, what caused the alarm. What do I do about it? And what action do I take to get to a safe state? And then there's going to be output devices. And I put the old walkie-talkies here to say, well, maybe the board operator is going to get on the radio, call out to the field operator and say, hey, the level is high. Can you go close this valve? And the operator out in the field might need to manually grab a hand wheel and move a valve to a closed position. So there are a lot of different pieces that aren't integrated into one whole. And furthermore, how do you put the PFD on this? Now we do, but this, really realistically, putting numbers on human actions is extremely difficult and extremely error-ridden. Okay, so if I have my LIPL, my non-SIS Sky, how do I develop the design basis? Well, what you can do is you can break the entire LIPL down into subsystems and assign a PFD to the subsystem that will allow the function as a whole to be able to achieve tolerable risk. So let's start out with the definition of an independent protection layer as we knew it back in 1993. So an independent protection layer, generally, if you're using order of magnitude math that was prevalent before LOPA 1991, you would say that an independent protection layer is going to give me at least one order of magnitude of risk reduction. That's going to be a risk reduction factor of 10. That's going to give me a probability of failure on demand of 10%. PFD of 0.1. So, but you have to remember that that 0.1 is for the entire function, not just the little tiny subset of the function that I'm using at. So what PFD, if I'm going back here to this item, and I want to design this piece, okay, that's great. I know that the whole thing is going to be a PFD of 0.1, but I don't have this entire budget to design just the sensor. So what do I do in that case? Well, you could do this. You could do a detailed fault tree analysis. What do you guys think? Does everybody want to do a fault tree, replace your LOPA with a fault tree for every scenario where you're going to do a detailed quantification of the sensors, the logic solvers, and the final elements of all of the subsystems? Well, sometimes you do need to go to this level of detail, but it is extremely rare. So very onerous. Doing a fault tree like this is probably going to take a day of effort. Are the results worth the cost? Is it practical to do this? Well, I've done some webinars where I say for some situations, going to this level of detail absolutely makes sense. But 99% of the time, it does not make sense to go to this level of detail. So how are we going to simplify things? Okay, so we're going to go into our LOPA and we're going to say how much credit was given to the IPL. And then we're going to take the budget and assign it to different pieces of equipment. So if I say that my alarm has a PFD of 0.1, you might be ignoring important things like what's the probability that the operator isn't aware of what the hazard is that's associated with the alarm? What is the probability that the operator just doesn't realize that they need to respond? What is the probability that the operator doesn't do the right thing when the alarm comes in? These all need to be given some sort of probability budget so that we could focus on the equipment design. So what is that budget? For independent protection layers that, or a portion of an independent protection layer that is not a complete function, each subsystem can be given a budget of the total PFD. And there is no right answer to this, but there are rules of thumb, and the rules of thumb come from the manufacturer's standard. So if you go into IEC 61508, you'll know that a transmitter vendor can get their device certified to SIL 2. Well, how do you get a sensor certified to SIL 2 when it's not the whole loop, it's just a part of a loop? Well, the standard is going to give some rules of thumb as to how much budget you're allowed to have. And the budget is 35% of your function is going to be in your sensor. 15% of your budget is going to be in your logic solver, and 50% of your budget is going to be your final element. Now, you might want to diddle with this because logic solvers are generally really, really good. Sensors are generally really, really good. And final elements are really, really bad. So what happens in the real world is that this is usually less than 1%. This is less than 1%. And this is greater than 99%. So I'm going to recommend that you stick with the budgets that are contained in 1508, but you can give yourself some flexibility. There's nothing that is required, so you have to use some judgment what makes sense for your plant. So then you're going to calculate a PFD for your subsystem that's going to be less than or equal to the budgeted PFD. Now, some of you are probably grumbling, oh my God, no way, Ed, I am not running SILCalcs for every alarm that I have out there. Non-starter, not going to happen. Shut it. I'm tuning out. Don't panic. I've got an easy way for you to do this. It's just a real quick and dirty lookup table that's going to be at the end of this. But I need to give you all the background on why that lookup table is going to work for you. Okay, so kind of going back, you guys know the PFD calculations. There's going to be three more terms out here, but the only one that we're really worried about is the DU term of the PFD equation. So the probability of failure of my device, whether it's a shutoff valve or if it is a sensor, is going to be lambda T over 2. So yeah, that's how we run SILCalcs. No magic there. Everybody's seen that. So we can calculate the PFD of this. So we know the PFD of the subsystem. We can figure out what the lambda is and figure out then, based on those numbers, what is the maximum test interval that I'm allowed for that type of device. So let's take a look at if I'm just generating an alarm with a pressure switch. So let's say I have a LOPA, and the LOPA is going to take credit for operator intervention based on an alarm, and the alarm is generated by a pressure switch. So my operator intervention IPL has a total budget of 0.1 because that's what my assumption was in the LOPA. And even if you didn't do a LOPA, you only did a HAZOP, we don't take credit for everything. So there's kind of even back before LOPA existed, a kind of a tacit assumption that a protection layer better be getting me 1 order of magnitude of risk reduction. So it's a very common approach. Now, I've got 1 order of magnitude total, but my sensor only has 35% of that budget. So my PFD max on my sensor subsystem needs to be 0.035. So then I simply figure out, well, if I have a test interval of 1 year and I went into my database, maybe I went into my Kenexis SIS engineering handbook and went to the tables into the back and found a number for a generic pressure switch. And I calculated that my PFD is 0.017. My budget was 0.035. I'm good to go. I met my target. So that was for a sensor. For a ball valve, a valve, any type of shutoff valve, you're going to do the same thing. So if I need to push a button and have the valve go closed, just looking at the valve portion itself, you're going to give yourself 50% of your PFD budget. And you, again, find a number that you can use as a DU failure rate for a valve. You put in a test interval. And my PFD I calculated here was 0.005, which is an order of magnitude better than what my target was. So I'm good to go. Now, what I'm going to do, and Chris, All right, this is something, I have a quick table here, but there is a paper that we wrote as part of this presentation that goes into a little bit more detail that, Chris, if you could, when you put together the web page that includes a link to the recorded webinar, make sure that that page has a link to the paper that everyone will be able to download. Just make a note for yourself for that.
Okay.
Okay, so what we did was we said, okay, well, what are the different common alarms that we're going to have? What are the different common final elements that we're going to have that are our SCI, our non-IPL protection layers? And let's just do a lookup table that says, what is the maximum test interval for a generic device that is going to allow me to achieve either 35% of a 0.1 budget or a 50% of a 0.1 budget, and still be able to achieve our SIL targets. So for an old float type level switch, if you test it more frequently than once every 3 years, you're going to be able to achieve 0.035. If you have a typical generic pressure transmitter, you could test once every 5 years, and so on. So these are all generic numbers. And the way that we at Kenexis do our generic numbers is we look at a category like differential pressure. We'll accumulate data from equipment vendors. We'll accumulate data from data sources like Orita. As a matter of fact, I did an entirely separate webinar on how Kenexis develops generic data. If you're really interested, go look at our archives. You'll be able to see that. But we just took those generic numbers and ran calculations to figure out what is the maximum test interval that that device is capable of without exceeding its budget for its portion of the safety instrumented function. So what you're going to have is you'll be able to download a lookup table that tells you what your maximum test interval is, and then you need to make your test more frequent than whatever that maximum number is. So a little bit more information on testing considerations. You'll notice that we only ran the DU term. We did not run the DN term. Now, that's this. It's a more simplified approach, but we're assuming that you are doing a full functional test with a manual proof test coverage of 100%. If it is not, if you're just running AutoCal on the transmitter, you're just pushing in a 4-to-20 via the heart communicator, that's not a manual proof test coverage of 100%. And my very simple answer there is, redo your test process. I want a good test. Yeah, Chris, there's a question.
Yeah, one in the chat here. Do these tests define the type of test, FFT or partial?
These are full tests. It has to be a full, complete 100% test. If you want to do a partial test, your math is more complicated because, again, our quick and dirty lookup table is full functional test, 100% proof test coverage. If you want to do something less than that, well, it's up to you to run a more elaborate calculation with diagnostic coverage for a partial test, manual proof test coverage for the full test, and so on. So our quick and dirty lookup table assumes full functional test, 100% manual proof test coverage. Okay, after once you kind of thought through the process, you're going to need to write yourself a test plan for the full functional test. And that test plan should be written in a simplified generic way so that it applies to every device of that type. So you're going to have one test plan for differential pressure level measurements that you're going to use for every differential pressure measurement of those low integrity protection layers. Yes, Chris, another question, I guess.
Yep. Does a safety critical element need to be credited in LOPA? Could it be a safety critical element if only credited in HAZOP and not LOPA was required according to corporate guidelines?
The corporate guidelines is the most important statement that you said right there. The original standard doesn't distinguish between how you determine what is safety critical and what is not. And I'll get into the LIPL standard because the LIPL standard, the new one that was just released, goes into a little bit more detail. But the original ISA 849101 simply says you need to determine and document what is safety critical without giving you a procedure for how do you do that. And when that happens, that means it's up to each individual operating company to decide what to include into that safety critical element list. Now, HAZOP LOPA is a very common way to do that, very well-defined way to do it, but it's not the only way to do it. For instance, a lot of operating companies will also include all fire and gas detection equipment as safety critical elements, even if the LOPA never recognized the fire and gas equipment as safety critical. So it's completely up to the operating company and what their procedures are for identifying and classifying everything that is a safeguard. There's no, the only standard says you need to determine and document, but it does not tell you how. It's up to each individual operating company. The most common way, though, is the HAZOP LOPA safeguard approach. All right, next question.
Does a safety critical element need to be credited in LOPA? Could it be a safety critical element if only, I think you answered the question.
Yeah. There are a lot of different approaches. So, different safeguards are brought in by different studies. So kind of if I could go, kind of a little bit off topic of what we're doing, a fire water pump is a safety critical element for sure. But there's no LOPA scenario where the fire water pump is going to be a safeguard. So for the alarms, absolutely, that's going to be the place. For the push buttons that close valves, most of the time you're going to see that show up in a HAZOP or a LOPA. But there are other things that are often considered safety critical that aren't going to be credited this way, and you're going to need to come up with different approaches. So primarily the discussion that we're talking about today is going to be related to push buttons and valves and alarms, and those generally will show up through that HAZOP LOPA workflow, but not always. And if a push button shows up as a result of a fire and gas mapping study instead of a LOPA study, it's up to your corporate standards to make the determination which studies result in SCEs, safety critical elements. Okay, so we're going to write one test plan for every category of equipment, And then we're going to record our failure data that we use in our calculations. And you can either refer to the Kenexis paper, or you could write your own document to attach into your corporate standard that defines these test intervals. Okay, so some conclusions, and it's conclusions for the PowerPoint section of the presentation. I've still got more to go, but conclusions from 15 years ago: all safety critical instrumentation, even non-SIS, needs to be tested at some interval, and this is a requirement of law, or it has the weight of law from the regulators. In the US, that's OSHA. In other parts of the world, it's other regulators. If you have safety critical instrumentation, you need a mechanical integrity program that includes how often you're going to test it. Absolutely critical. Now, the methodology in TR 8402, this is the SIL verification technical report. It tells you how to determine how often you should be testing something as a function of what's the probability that I can allow it to fail and the other attributes of the device, like the failure rate. But in order to do this, you're going to need to do some budgeting, because you don't have the entire budget available for every instrument that's part of an independent protection layer. So the test interval that you're going to apply to those valves and to those sensors is going to depend on the failure rate of the device, and making your time easy, run one calculation for a generic component and apply it to everything in your plant instead of running each one separately. So it's a function of the failure rate and the target. And the target is generally going to be 0.1 for one independent protection layer spread out. So utilizing this method, 2-year test intervals or longer are possible. So you have to remember, when we wrote this paper, a lot of plants were new to process safety management, and they were still trying to test once a year. And we're like, whoa, hold on. You don't need to test once a year. Your instrumentation is better than that. You can justify a longer test interval than annual testing. Now, always you're going to need to verify what that test interval is, and whoever the people in your organization who understand PFD failure rate are the people who are going to need to write the standard for you. Now, you would think that we're done because I just finished the conclusion slide from the presentation, but this conclusion happened a little bit more than 15 years ago. And yeah, Yasser is from Zadco, or ADNOC Offshore, was the guy who forced me to develop all this stuff back in the day. So great guy. I don't know if any of you know Yasser Khalil. What I'm going to do now is I'm going to try to bring you up to date by going into a very little bit of detail on the draft version of the new LIPL standard. So you remember that the standard I showed you at the beginning was 84.91.01. And that standard is still pretty close to what it originally was, which is a standard that says you, the end user, need to determine what is safety critical and document what is safety critical. And if it is safety critical, you need a mechanical integrity program that includes testing and resolution. And that program needs to be consistent with recognized and generally accepted good engineering practices. Well, as the years progressed, in the US, I'm going to bring the discussion back to the US, our regulator is OSHA, the Occupational Safety and Health Administration. they noticed that some operating companies were doing shortcuts. So instead of having a SIL1 safety instrumented function, they would have a BPCS interlock. And because it's a BPCS interlock, I don't need an SRS. I don't need any SIL calcs. I don't need to test it because it's not a safety instrumented function. So improper. I'm not supporting this. I'm just telling you what happened, and I'm violently opposed. The OSHA regulators came up with a term called they loped away the requirement to do testing. So basically, they used LOPA as a tool to not test safety critical equipment because they basically in the LOPA said, well, it's not a safety instrumented function, so I don't need to document it. I don't need to test it. This started happening even as early as 1996, 1997. It got really bad in the early 2000s. And now it has come full swing in the other direction where OSHA and the U.S. Chemical Safety Board said there are accidents that are happening. People are dying because you are calling something a BPCS interlock. You're not testing it. You're calling something a safety critical alarm. You're not testing it. Those devices are failing and people are dying. So we need to do something different. And back in 2017, 2018, these standards take a long time. We started to write a technical report, which is now a standard for low integrity protection layers. So what we wanted to make really clear is if you take credit for something in your layer of protection analysis, it is safety critical, and you need to have a mechanical integrity program, which means you need to document, you need to test, you need to resolve testing issues. That is the purpose of this standard. And the way to think about this is the IEC 61511 life cycle for everything that is instrumentation but is not a safety instrumented function. That's the easiest way to think about this. Now, the people from the ISA 18 committee, bless their hearts, are going to do everything to tell you that alarms don't apply. You can make your decisions for yourself. I think that this is an excellent approach for designing alarms. Yes, Chris.
Question here. How can I define if I need to execute a proof test to the whole loop or just a simple element of the SIF at a time?
Well, it would be the answer to that would be, how do you define your loop? But if your loop contains an operator in the middle, you can't really test the operator. So you're going to need to test the individual subsystems. And if you go back and you look at IEC 61511, it allows you to test your loop in parts. So you could test the sensor today, the final elements tomorrow, and the logic solver next year. So I would, again, recommend breaking your IPL into subsystems, giving a budget to each subsystem, and then running your tests on the subsystems. So if you have a operator response based on an alarm, and your total loop includes the alarm, operator, detecting that the alarm occurred, calling out to the field operator, and having the field operator manually close a hand cranked valve, I would treat the alarm through the enunciation as one subsystem with 35%. I would actually treat that manual valve as a safety critical element. And, require basically, function testing to, during the turnaround, have the operator go out to the field and actually move that valve and make sure that it'll move. So yeah, there I wouldn't run a PFD calc on a manual valve that you're moving with your hand. But making sure that the test gets done, I absolutely do see value on that. So I would break it down into the most reasonable subsystems. Okay, so kind of going into 849103, it talks about what these low integrity protection layers are, and it's basically everything that's not a safety instrumented function that includes instrumentation. And these they're called low integrity protection layers because the PFD requirements are less than SIL 1. Most of the time, the risk reduction factor is going to be exactly 10, and the 61511 standard is SIL 1 begins with greater than 10, so 10.0001, but not 10 exactly. So it goes in the standard, if you look at it, is going to go into a lot more detail, and it's going to lay out. I don't want to go to the detail of calling this a full SIS safety life cycle, but it's going to give you steps. So you're going to need functional safety management. You're going to need to plan how you're going to treat alarms and push buttons and valves. You're going to need, oh, there we go. We have actually a little bit of a drawing. So you're going to need to identify and classify all of your low integrity protection layers. You're going to define requirements. You're going to do a detailed design and implementation, and then operate, monitor, and include those low integrity protection layers in your management of change process. So just because you say something is not a safety instrumented function doesn't mean you're allowed to ignore it. No, you have to write specifications for it. You have to test it on a periodic basis. The only thing that this does not require you to do is run a calculation. But at the same time, how do you know what test interval you should use unless you've run a calculation, or you just simply use the Kenexis lookup table to determine what the maximum calculation would be? Yes, Chris.
Has this become live yet, or when do you expect it to become live?
It is approved. So this standard, and I'm showing you the version from January of this year. We did a vote, and it was approved in the February timeframe. A lot of people from the ISA 18 committee tried to get the vote revoked, and you can't do that. So it's approved right now, but it has not. I don't think it's been released. I'm going to need to do a follow-up when we publish the recording of this webinar to determine whether or not it's actually been released as a standard. But it is approved, and it's just a matter of the paperwork of having ISA issue it. Imminent, like it could already be released, and if it's not already released, it'll be a matter of weeks or months before it is released. Okay, so again, I just kind of skimmed through some of the requirements, and basically this is IEC 61511 light for everything that is not a safety instrumented function, but is instrumentation. So now we finally have a basis for how we make decisions about non-SIS independent protection layers. So with one last thing to kind of show you some best practice, let me come back in, and I'm going to go to the Kenexis Integrated Safety Suite. And many of you are familiar with the General Oil and Gas Operating Company Texas City gas plant. I'm going to go to the separations area, and you'll know that I have a HAZOP study. Actually, is this? You know what? I don't remember which one it is that I'm working with, so bear with me for a second. But you'll know that when you do your HAZOP, sometimes you're going to go into a LOPA for whatever reason, whether it's the risk is high, the consequence is high, a safety instrumented function is one of the safeguards, whatever reason, you'll go into a LOPA. And in LOPA, you will take credit for things as safeguards, and some of those safeguards might be alarms, some of them might be basic process control loops, some of them might be push buttons and valves. So you're going to have a list of everything that you took credit for in your safeguard list. So what we recommend for compliance with the LIPL standard is very similar to what you would do for an SIS. So you could go into premium tools and you can synchronize with Vertigo and you could create a study that's dedicated to your alarms. I've already done that, so let me just back out and show you what this would look like. So here you're going to, and I just linked one of them so you could see that this is linked to my HAZOP study. So it's an alarm in the PHA, Open PHA. It's an alarm in Vertigo. And you're going to have a performance target associated with the subsystem. So in this case, I said my performance target for the alarm is a risk reduction factor of 30. And my device is a pressure transmitter generic. And in this case, I ran a test for 60 months. If you go to this level of detail, you can even do something crazy like put in, imperfect testing of 95% and a useful life of 30 years, and we'll see if we still meet our target. To hit update there, and we no longer achieve our target when we considered imperfect proof testing. So if you use this mechanism, you have everything in here. So if I go into pressure transmitter 104, I can come in and I can do my data sheets the same way that I would if it were an SIS instrument. And then I will also be able to keep track of all of my testing of this device, just as if it were a safety instrumented function. So the new ISA 849103 standard is going to put more requirements on you for these alarms, for these safety critical valves, because you need to define them, you need to document them, you need to test them, you need to keep track of your testing for these devices. It's just that the level of effort is lower, the number of requirements you need to meet is smaller, and technically you don't even have to do a SIL verification calculation, and you can make that SIL verification based on a lookup table. You can run the calculation if you want. Just make sure to give yourself a target that is a portion of the overall budget, not the budget for the function as a whole. And with that, that is probably an hour longer than anyone probably could have ever expected that anyone could talk about this topic. And yet I did. But with that, I'm going to go ahead and open the floor now. I know that I got some questions during the meat of the discussion, which is where I like to answer the question. But I will open the floor now to any other questions that anyone might have on the topic of low integrity protection layers, setting test intervals for non-SIS safety critical equipment.
I don't see anything in the chat at the moment. Does anybody have anything?
Vincent, question.
Will ISA 849103 provide any guidance or teeth on proving that that human logic solver is meeting that 0.015 budgeted portion of the PFD?
No, it will not, because we are the instrumentation and control group, not the operations team. Now, a good LOPA process should include those considerations. So when you're, let me back out of here and bear with me for a second. If I go to let me come back here to my LOPA scenario. So I know that this alarm is being used in scenario 1111. If I click back here and look at it in the LOPA worksheet, this is my LOPA scenario that includes this. Now, when you're in the LOPA study, there should be an IPL rationalization process, kind of a question and answer framework that you're justifying yes or no, can I take credit for this as an IPL? So some people might do that during the LOPA study itself. A lot of people are going to pull up this safeguard list after the study and do a separate rationalization process where they will go, and let me make this a little bit clearer. So if I were doing an IPL rationalization, I would expose more of these fields. I'll just show everything. And now you'll see that this worksheet got a whole lot bigger. And you can do things like you could say, all right, is it independent? Is it auditable? Is it effective? And the workflow for making these determinations is going to include how much time does the operator have to respond? Is the operator trained? Is this alarm in our alarm manual? Did it go through the alarm rationalization process? Are there records that show that the operator was trained in how to respond to this alarm? How much time does the operator have to respond to this alarm? So there's a lot more that is done, but IEC, ISA at some point in time has to try to stay in its lane and say that, well, the hardware, the design and testing of the hardware, that's our lane. The decision as to whether or not we should be able to take credit for the operator, well, that's Center for Chemical Process Safety, PSM Group, LOPA's lane. So maybe not a satisfying answer, but that's the best I could do for you.
Yep. I guess you had to assume that 15%. And personally, I'm an EPC guy, but that sounds low. I would think that failure of the operator would be higher than 15% of the time. Compared to the other pieces.
Let's pull on that for a second, because if you want to really get lost, you can read some books on calculating human failure rates, but human failure is so dramatically tied to what you're doing that the probability of failure is somewhere between 1 in a trillion and greater than 99%. So let's look at an example of something that fails almost all the time. Back checking someone's work. So I run a calculation. I hand that calculation to you to back check it and make sure that I did it wrong or did it correctly. If I did it wrong, the probability that you will fail to detect that I did it wrong is close to 80%, maybe higher. 80% of the time, you will not detect that I did it wrong. The reason is I always get it right. You assume I'm going to get it right, and that's your position going in. That's your frame of mind when you're looking at it. So the probability of failure is extremely high. Now, let's look at something else. if I get in my car, make a right turn, I'm going to get to the intersection with Fishinger Road in about a mile. What is the probability that if I see a red light, I'm not going to stop? It's not 50%, I can assure you. It's not 10%. If it was 10%, there would be an accident at every intersection in the world every time the light switches from green to red. That probability of I'm coming to an intersection, the light's red, what's the probability that I don't stop, is actually probably close to 1 in a billion that you will get it right or that you will get it wrong. So it's very tightly based on what you're doing, how much time you have, what are the consequences of doing it wrong. And we've got data from Sandia recovery model is one of the best models for this, that say that if a human operator has got, low stress, well-trained, 10 minutes to respond, the probability that they misdiagnose something is around 1%. It's probably going to be less than 1%. Now, I'm going to give you the caveat that the Sandia recovery model is based on simulators of nuclear power plant operators. And nuclear power plant operators get trained a whole lot better than chemical plant operators. So probably not as good, but 10% is a very conservative high number for an operator not responding to something. And again, it all depends on your plant. How many alarms did they receive in the last 30 seconds also is going to drive that. All right, Chris, any other questions?
Yeah, we got a few things here. One being, for a SIF, once it has been completely tested during the commissioning, do we need to periodically test the program logic if we can prove that the logic has not changed since the commissioning?
No. That's the short answer. You don't need to test the log. Okay, this is a whole other topic about the frequency and the thoroughness and the procedures for testing logic solvers. I don't feel the need to test logic if the logic has not been changed. So when you're doing a site acceptance test, you're going to want to test every aspect of the logic. How do you respond to bad PVs? How do you respond to bypasses? What are all the combinations and permutations of all the voting arrangements? Absolutely, during the SAT, you want to test that. But from that point in time on, if the logic doesn't change, you don't change the configuration, you don't change the software, then the logic can't fail because it's not changing. But that doesn't mean that the hardware that is executing the logic can't fail. So how do I test to make sure that the logic is still, or that the hardware is still working? Well, your logic solver vendors have a whole lot of ways to test the logic, test the hardware to make sure that every bit in memory, every resistor, every transistor is working properly. A lot of that is done in automatic diagnostics to where you don't need to test it but once every 10 years, 15 years, and still achieve your SIL targets. And they're better at it. So, a lot of what I would recommend on a logic solver is please coordinate with your equipment vendors. They have service technicians that when your plant is shut down, they will be able to connect test equipment and literally test every bit in memory of every memory location in your logic solver to make sure that all your bits and bytes are working. None of your resistors have failed. And if they have, they can go in and replace failed components, probably at the board level. But that's a more elaborate way to test the hardware. And that test of the hardware is completely agnostic of the logic that's being run in the hardware. So being able to turn a bit in memory on and off to be able to invert memory maps, none of that is reliant on the actual logic that you're executing. So the testing that the logic solver vendor can do to make sure that your hardware is 100% functional is agnostic to the code that it's running. And if you don't change the code, a failure isn't going to just materialize out of thin air. So I'm probably a little bit more on the side that says, if I passed the SAT and I have not changed the logic, then my testing on my periodic tests needs to focus on dangerous, undetected failures in the hardware, as opposed to checking to make sure that the logic didn't change. Checking to make sure the logic didn't change should be a simple matter of looking at the revision that's running versus the revision that you think should be running. Dave, question.
I'll just kind of voice the question that I put in the chat, but when we were talking earlier, and just to kind of follow up on the PFD and the allocation of the 15% for the human, component of the logic solver, or the loop here, you're talking that, the PFD that's needed overall by the LOPA designation is 0.1. That's for the entire loop,
Yep.
including sensor, logic solver, final element. In this case, the logic solver is a human, so we really only have 15% of 0.1 to allocate to the human.
That is correct. Yeah, it's what, and now you start looking at that, you're like, oh, I was assuming that there's a 10% probability of failure that my operator gets it wrong, when really it's a 1.5% probability that the operator makes the wrong decision. And I have to account for all the other bits and pieces of the loop, which might include things like, are my walkie-talkies working? Is the board operator going to be able to call out to the field operator? Is the field operator actually there? Are they going to be able to get to the valve? All this stuff gets thrown into that piece.
So if you've, say, for example, you take the standard, CCPS LOPA book value for operator intervention to an alarm, where you've, got all your emergency procedures and all the things that are required for a standard 0.1 human response to an alarm, that would be a 100% allocation of your PFD to the human error component. And realistically, you couldn't take one order of magnitude credit for that alarm loop if you didn't have, I guess, a less than 0.1 component for your human, right?
Yeah. That's it. The budget has to come from somewhere. The operator intervention based on an alarm includes the alarm hardware, the transmitter, and whatever's enunciating it. It's going to include the operator, the human being. It's also going to include whatever action we need to take to get to a safe state. All that stuff summed together is the 0.1.
Okay.
Yeah,
it includes the sensor and the final element. I was thinking that the 0.1 only applies to the human, for example, not the entire loop.
No, it's necessarily everything. Otherwise, your hardware can't fail. If you give 100% of the budget to the human, your hardware cannot fail, which that's also unrealistic. Yeah, maybe some serious food for thought here on, wow, should I be giving as much credit as I am giving to those alarms? There's a lot to it.
And with that, we'll go ahead and end today's session. Thanks again, everyone.
Thanks all.